In this video, we are going to discuss 4.6, which is solution stoichiometry and chemical analysis, otherwise known as titrations. So if we can easily convert between moles and volumes using molarity, and the question we really want to think about is what do we want to do for reactions that are in solution? And so it's a combination of molarity, reactions, and kind of a limiting reactant. So when we think about a titration, we can use this sample here. What we see down here is our analyte, or the unknown. Up here, we have the known. And so we can ask ourselves, how do these create an equivalence point? And so the trick is to think about a titration like this. So we start here. This is our unknown. And then you're going to add or titrate in the second. In this case, we have stars and circles. So we're going to add circles, and we're going to add more circles until we reach the equivalence point. So the equivalence point, this is the point when, in our case, stars equals circles. And so at that point, they are even. If you were to have acids and bases, the acid, that's not how you spell that. The acid protons equal the base, units. So at the equivalence point, the number of protons and the number of base units is equivalent. So the trick is to think about this along this pathway. So if we have the volume of our standard solution, so this is the, for example, our goal is to find the unknown concentration. So if we know, going back to this image, if we know the quantity of red circles, and we know the solution that they came out of, we can back calculate the number of blue stars. So at the end, we can see that they're both 7. But that has to be with all of the compounds, and so it matters whether it's a 2-to-1 ratio or a 1-to-1 ratio. So in this graphic, the volume of standard solution can be converted. So if we have a volume, we're going to use molarity to determine the moles. Then we're going to use the balanced equation to determine the moles, and then divide by volume to find molarity of unknown. So all of this is to tell us that we can do these complex titration questions. Now, titration questions feel scary. I get that. But it is a series of steps, which if we think about it, it's 1, 2, 3 calculations. These 3 calculations are very simple and are very similar to determining the limiting reactant. We just also have a volume. So, in our first example, if 45 mils of hydrochloric acid is neutralized by 35 mils of 1.22 molar sodium hydroxide, what is the concentration of the hydrochloric acid? So the first thing we need to do is to figure out a balanced chemical equation. So HCl plus NaOH If we think back to a metathesis reaction or an acid-base hydrolysis, we see that we get sodium chloride and H2O. And so this equation is balanced. So it's a 1-to-1 ratio. So the first thing we want to do is use the known hydrochloric acid. So this will be, yikes, equation part number 1. We're going to take our 1.22 moles per liter. Now, this right here, if you remember, molar equals moles per liter. I just took the molar back into moles per liter so that I could multiply it by the volume, which is 0.035 liters. And so when we multiply these together, we get 0.0427 moles of NaOH. So the second step is to convert moles of sodium hydroxide into moles of hydrochloric acid. So the moles of NaOH, then using the stoichiometric coefficient of 1 mole of NaOH is equal to 1 mole of HCl. Whoops, forgot the L. Gives us 0.0427 moles of HCl. So the third and final step is to determine the molarity. So we know that our previous volume is 45 mils. So we're going to take our 0.0427 moles of HCl divided by the total volume that we started with, which is 0.045 liters. And that gives us a molarity of 0.94889 molar. But we probably need some sig figs. So all of the values in our equation only have 3 significant figures. So we will pair this back to being 0.949 molar. Oops. So this feels quite complicated, but we just convert the first step, we're going to convert using the molarity and the volume to determine the moles of sodium hydroxide. Once we determine that, we can use our stoichiometric ratio to convert to the moles of hydrochloric acid. Then we can divide by the volume that we started with, and that will give us our final molarity. Let's work another example. So in this example, one method to peel potatoes is to soak them in sodium hydroxide for a while and then remove the peel. The sodium hydroxide concentration ranges from 3 to 6 molar. In a solution analysis, 45.7 mils of half molar sulfuric acid is required to neutralize 20 mils of a sodium hydroxide solution. What is the concentration of the sodium hydroxide solution? So we're going to, again, take our 3 steps. Step 1, convert using the molarity and the volume to moles of sulfuric acid. Wait, we've forgotten the most crucial step. We need a balanced chemical equation first. Sodium hydroxide plus H2SO4 gives us Na2SO4 plus H2O. So this is unbalanced because there are 2 sodiums here. So at this point on the left, there are 4 hydrogens and only 2 on the right. So we will add a 2 here as well. So in this case, we have 2 base units for every 1 acid, or 2 moles of base per 1 mole of acid. So from here, we now need to return to step 1, where we take our 0.500 moles in 1 liter, multiply that by 0.0457 liters. which gives us 2.28 times 10 to the negative 2 moles of H2SO4. Now we're going to use our second plan, which is to convert the moles of sulfuric acid to the moles of sodium hydroxide. So if we have 2.28 times 10 to the negative second moles of H2SO4, the stoichiometric ratio is 1 mole of H2SO4 for every 2 moles of NaOH, which gives us 4.56 times 10 to the negative second moles of NaOH. We're running out of space here. 3, we're going to divide our moles of NaOH. Actually, we'll just do this right over here. We're going to divide this by the volume of 0.020 liters, and I got that number right here in the question. And so then when we plug this back in, we get that it is 2.28 molar NaOH. Ignore the next example. We're not quite there yet. So what we see is that it's a series of 3 calculations. You can do it all at once. You can do each one at a time, but you don't have to stop on each one. So let's look at another example. So in this case, we'd like to know how many grams of calcium hydroxide are needed to neutralize 25 mils of 1 molar nitric acid. We're going to need a balanced chemical equation. So we're going to have our HNO3 plus calcium hydroxide gives us calcium nitrate plus water. So in this case, we see that our calciums are balanced, our nitrate is not. So we'll add a 2 in front of the acid and a 2 in front of the water. So we have a balanced chemical equation. So now we can begin our calculation. So step 1 is to determine the number of moles. So we have our 1.00 moles in 1 liter times 0.025 liters, which gives us 0.25. Whoa. 0.025 liters. Moles. So in the next one, we're now going to take our moles of nitric acid and convert that to moles of calcium hydroxide. So 0.025 moles of HNO3, there are 2 moles of HNO3 for every 1 mole of calcium hydroxide, and that gives us 0.0125 moles. So now we're going to use a calculation that we're very familiar with, where we convert moles to grams. 0.0125 moles of calcium hydroxide multiplied by 1 mole of calcium hydroxide has a molecular weight of 74.10 grams. When we plug this in, we get 0.92625 grams, which feels like too many sig figs, so we need 3 sig figs of 0.926 grams. So in this equation, this one, again, it's still just 3 very simple steps where we convert to moles, then we convert to our second type of moles, and then we convert to the molarity or the grams, depending on what it asks for. So we will do one more example in this video. In this case, this one's a little bit different. So a sample of iron ore is dissolved in acid, converting the solid iron to iron 2+. The sample is titrated with 47.20 mils of 0.02240 molar manganate ions using the following balanced equation. So in this case, there are three questions. How many moles of MnO4 were added? Well, we have the molarity and the volume, so it's relatively simple. So I'll title these 1, 2, 3 so that we can go looking for that a little bit further down the page. So in equation number 1, we're going to take our molarity, split it out, and multiply by the volume. There are 0.02240 moles in 1 liter, and we're using 0.04720 liters. In this case, that gives us 0.001064 moles of manganate, MnO4 minus. So that's a relatively simple common calculation. So it asks how many moles of iron, 2+, were in the sample, and how many grams is that? If we're going to take our 0.001064 moles of MnO4 minus, using our balanced chemical equation right here, we can see that for every 1 mole of MnO4, there are 5 moles of iron 2+. So when we solve that equation, we get that there are 0.005320 moles of Fe. To convert that to grams, and 1 mole of Fe, there are 55.85, which gives us 0.2971 grams of iron. Whoops, that's totally missing. So we've answered part 2. So part 3 asks if the sample had a mass of 0.8890 grams, what percent iron is it? Well, we know that the total amount of iron is this 0.2971 grams. So in part 3, we're going to take our 0.2971 grams of iron, divide by the total mass of 0.8890 grams, multiply that by 100, and that gives us 33.42% iron. This was a titration too. So it gave us the titrant here. And so in this case, we could have answered this question all at once, but we stepped through it one at a time. So as a reminder, titrations are a simple concept where we have a starting point with the unknown concentration. We don't know how many blue stars there are, but we do know how many milliliters it is. Then we add in the red circles until we reach the equivalence point. And we can identify the equivalence point like you will in lab using something that's called an indicator. They usually change colors. And when you do that, by knowing the amount of red circles that you added or the number of mils of that, we can then determine or back calculate the starting concentration.